Okay, if you're still coming in, please take your seats. We should get started soon. Okay, welcome today. It's so nice to have everybody back. It is my pleasure to introduce our speaker today. This is Professor Daniella DellaGiustina from the University of Arizona. Dr. DellaGiustina is the PI of OSIRIS-APEX. She's the deputy PI of OSIRIS-REx. She is a co-I on the Artemis 3 LEMS. That's the Lunar Environment Monitoring Station. It's a seismic activity monitor, clearly. She is also a science team member, of HERA and MMX. It is my pleasure, so please join me to welcome Professor Dani DellaGiustina.
Thank you, Shannon, for that kind introduction. Okay, the screen is fully above me. That makes this easy. So I do a lot of random things, but I'm really pleased today to talk to you all about the OSIRIS-APEX mission, which is a planetary exploration mission that is visiting asteroid Apophis shortly after it makes a close encounter with the Earth in 2029. But I'm also excited to talk a little bit about the OSIRIS-REx mission because we are basically getting to recycle the spacecraft that was used for OSIRIS-REx in order to do this follow-on mission. And so I also got a lot of questions today as I was meeting with various people about some of the latest results from OSIRIS-REx. And so I thought, okay, all right, I'll add in a couple of slides just to cover those bases as well. So I want to, there we go. I want to start off this talk by just framing some of the big overarching science questions that we have answered with the OSIRIS-REx spacecraft at its first target, a carbonaceous asteroid called Bennu, and then what we hope to answer going forward as well. And just talk a little bit about our motivation for studying solar system small bodies, in particular these small rubble pile asteroids. Like, why is NASA sending $1 billion spacecraft to study these objects? And then I'll talk a little bit about OSIRIS-REx to frame the capabilities that we will have going into our next mission, which is the OSIRIS-Apophis Explorer or OSIRIS-APEX mission. Okay, so just a little reminder about why we study asteroids in the first place. And in particular, we're lucky to have a reservoir of asteroids that are very energetically accessible to us in near-Earth space. But all of these objects have been sourced from the asteroid belt, which resides between Mars and Jupiter, and exists in the location of the water snow line, where in the solar nebula, liquid water began condensing into ice. And so our present-day asteroid belt is sort of a fantastic pile of debris of a lot of different processes that happened across the disk during the earliest days of the solar system. And so in this area, we have objects that represent carbonaceous chondrite parent bodies. So these are objects that probably formed around 10 AU or so, and were dominated by a lot of volatile material. But also we see within these objects some of the earliest solids that were formed in the solar system, like the presence of calcium, aluminum inclusions, and chondrites, and that gives us a good indication that some of these early, very high temperature forming materials were able to migrate all the way out here, form these bodies that were eventually kicked into closer into the sun, and then catastrophically disrupted through collisions that give us our modern day asteroid families. And so I bring up the carbonaceous chondrites because the parent asteroids of these objects are very analogous to and include the bodies that gave rise to, or the body that gave rise to asteroid Bennu, which was the target of the OSIRIS-REx mission. So it represents material that formed in the outer solar system, migrated into the modern day asteroid belt, and then subsequently was kicked into near Earth space. And I'll talk about that a little bit more in a moment. But there's a lot of other asteroid families in this location of the solar system that represent different bodies that formed in different parts of the disk, or perhaps at different epochs. And so this also includes the S-type asteroids, or the stony asteroids, objects that are composed of higher temperature forming silicates like olivine and pyroxene. And one of these bodies is the parent of Apophis, which will be the target of our follow-on mission. So we have this, we're quite lucky because, or unlucky, depending on how you want to think about it, because if you look in green, you can see the location of the asteroid belt right here. You can see that each dot represents a main belt asteroid. But we have a number of objects that have been kicked in from this reservoir to near-Earth space. And this is because if we go back to just looking at the overall layout of the solar system and where the asteroid belt resides, we have a number of mean motion resonances in this location with Jupiter that tend to kick material inwards. We also have secular resonances with Saturn that kind of provide a regular sort of process by which material can be transported into the inner solar system by ending up in one of these resonances. These objects typically drift into these resonances from some solar radiation effects like the Yarkovsky force. But as a result, there's a lot of material, a lot of objects, all shown here in red dots, that reside between the orbits of Mars and Venus. And these objects are both very exciting for us to study and also represent, potential hazards because many have Earth-crossing orbits. And so both of the objects that Bennu and Apophis, Bennu, which we have visited with our spacecraft, and Apophis, which we will be visiting, fall into this classification of near-Earth asteroids. They are composed of very different materials, but they're in a similar size range. They're both about 500 meters in their longest dimension, so you can think about their longest dimension being about as tall as the Empire State Building. And objects in this size range tend to be what we think of as rubble piles. So they're not necessarily monolithic bodies that have maybe just been battered by a long impact history, but they are loose, coalesced piles of rubble, boulders, rocks, etc., that are held together by microgravity. And so these objects are easy for us to study, easy for us to send spacecraft to. They're also hazardous, but in studying, in having the opportunity to study them, we really have the chance to look at a wide range of solar system processes, some from the various early days of our solar system's history to more modern day processes like space weathering. And so I haven't touched on everything that I include on this slide, but the way I often frame, why do we study asteroids in the first place, is because they hold a lot of answers about our past and about our future. Because they're these remnants of early solar system formation, we can study the processes that have taken place since the earliest days of the solar system by examining them. Some things that I will get into as I talk a little bit more about Bennu are that we have had indications for many years, and the evidence just continues to get stronger that asteroids, especially those of the carbonaceous chondrite, from the carbonaceous chondrite parent bodies, include a lot of material that is thought to be a precursor to life, and just some of the volatiles that needed to reseed the Earth early on in its history for life to arise and our oceans to exist. And then I have a feeling we'll see more and more of this story getting spun up with the changing tide in this country. But there are also incredible perhaps for resource utilization. A lot of stony and metallic asteroids, they represent reservoirs of platinum group and rare earth elements. And so, you know, there has been blips, I think, over the past 20 or so years that I've been in the field where asteroid mining kind of gets a swell of support, and then it kind of goes away, and then maybe there's a startup that's funded by, you know, that's well funded, and then it kind of goes away. So we'll see what happens, but I think commercialization of space is probably something we can expect over the next 30 to 50 years to a greater degree. And then, as I mentioned, asteroids have been responsible for some major extinction events in Earth's history. These are objects that have Earth-crossing paths through the inner solar system. And so for all of these reasons, we built the OSIRIS-REx spacecraft and launched it in 2016, really with framing the scientific objectives of that mission with, you know, we want to examine, study our past, and we want to understand our future. And this spacecraft, its key objective was to return a sample of asteroid Bennu, but it included a pretty fantastic set of instruments on board as well. And so I'll highlight our sample return mechanism, or sample collection mechanism, I should say, first. And it's basically a pogo stick. So it extends about 3 meters, and it was called the Touch and Go Sample Acquisition Mechanism, or TAG-SAM, but it had this sample collection device on the end, and you can see that close up in this inset. And the goal for collecting a sample with this mechanism was to basically allow the spacecraft to slowly descend to the surface of the asteroid. Once it made contact, once that outer edge made contact, and there was some amount of force exerted on the sampling head, then it would have triggered nitrogen gas to agitate the surface, collect some of that agitated material in the side of this outer ring here. So there's like a throat for the sample acquisition mechanism here. And then that was stowed in a sample return capsule, which you can see on sort of the center of the science deck. So I'll play some highlights from that sampling event. But the bottom line is that this was a very successful event, and the device worked not quite as expected, but that's only because the asteroid didn't respond quite as we expected. But we also have several visible cameras. So we had cameras of different fields of view on board the spacecraft, all built by the University of Arizona. And these were all in the visible wavelengths. So one had, MapCam has 4 color filters. We had 2 spectrometers aboard. These are just spot spectrometers, but they cover an incredibly wide range of wavelengths from about 0.5 to 100 microns. And so the visible and infrared, the OSIRIS-REx visible and infrared spectrometer is shown here, and the thermal emission spectrometer OTES is shown here. And then we had a scanning LiDAR contributed from the Canadian Space Agency. And all of these instruments are in great shape and ready for their next mission. Obviously, we used up our sample return capsule, and the TAG-SAM has been stowed away and probably won't work again because our heaters have been turned off. And we also had a student experiment named Rexus, but Rexus is no longer operational, so it won't be available for the next ride. Okay, so as I mentioned, we launched the spacecraft in 2016, and after about a 2-year cruise period, we arrived at asteroid Bennu in late 2018, and these were the earliest images of the asteroid as we were slowly approaching it with our spacecraft through our high-resolution optical imager. And so a couple things that stood out. One, Bennu looks like a rubble pile just by visual inspection, right? This looks like it's kind of a pile of rocks with maybe a little bit of structure here and there by created by some larger blocks. But all of everything that we had surmised about Bennu from telescopic observations, mostly ground-based, but some that we were able to acquire from space, had given us some indication that it would be covered in a relatively fine-grained surface layer. And so we were pretty, I don't know, we were surprised, and it wasn't pleasantly surprised when we arrived, because if you remember, this inset that I showed, our inner throat to ingest sample has this 3-centimeter opening. And so we did not find at first glance anywhere on the surface that had, an abundance of these small centimeter scale grains that we had designed our sampling mechanism to ingest. Fortunately, we did find a few candidate areas, and they were much smaller in size than we were designed to navigate to, but we patched our flight software. We found a way to navigate with even tighter tolerances, and this led us to sample a site called Nightingale in October of 2020. And this is what happened when we sampled. So this is from our SamCam. What you're basically seeing is that sampling mechanism with its sampler head outstretched as the spacecraft is descending downward. And we kicked up a whole lot of material when we interacted with the surface. So the idea of getting some, pushback from the surface, some normal force as we contacted it, it turned out to not work, because the behavior of Bennu's surface, it was so granular, it just behaved like a ball of pits, and a pit of balls, that one, like that you would see at like a McDonald's, playground, right? That's how the surface responded. And so we actually ended up syncing our sampling mechanism about to the length between my finger and my elbow into the surface before a timer kicked off, released that nitrogen gas, and allowed us to ingest a tremendous amount of sample. So much so that we were leaking sample before we quickly stowed it, because we had so many large rocks jammed in the throat of our sampling mechanism. So that was great. And we had the opportunity, after we stowed the sample, we backed away from the asteroid for a couple of months, and we made sure all of our systems checked out, and everything was in a good, safe state. We were able to then take another look at the surface of the asteroid and see what exactly had happened to the surface. How did it respond when our spacecraft completed this sampling event? And one thing that we learned through that, and this is relevant for what we plan to do with the spacecraft next, is that we realized we had unintentionally excavated a substantial amount of material with our thrusters alone. And so this is the point of the sample acquisition mechanism interfacing with the surface. But you can see there's some positive, so I should say that blue here indicates areas of excavation, and the warmer tones indicate areas where material has been deposited. So what you can make out here is that everywhere that our thrusters would have been perpendicular to the surface, we ended up excavating a fair amount of material. And this kind of gave us a serendipitous science experiment, because we know the force exerted by our thrusters onto the surface. And so by looking at how much material we had excavated, we could start to puzzle together, okay, what might be the surface strength? And then, of course, we had a really great data point from the actual touch of the sampling mechanism on the surface. But our spacecraft is designed as a sampling, as a sample return mission. It's designed to get really up close and personal to another object, a small body that's in the microgravity regime. And so we're excited to continue to do this type of experiment, but more intentionally. when we go to our next target. All right. So this happened in 2020. We departed in 2021. And last year in September of 2 years ago now, in September of 2023, the sample return capsule was released back to Earth. And we had a pretty more exciting than anybody wanted sample return event, but everything was a success. And these are actually some of our very earliest results, but since that point, since basically October of 23, we've been engaging in a comprehensive sample analysis campaign. So a lot of our earliest results, and really the stuff that is hitting the literature now, by and large, there's a couple of exceptions, but it came from material that was deposited on the avionics deck of our sample return capsule. And so if you remember back to that inset where I showed sort of the touch and go sample mechanism, the part that interfaced with the surface of Bennu, that is now on the down facing side of this image. This is the clamshell sample return capsule opened, and you can see that there's a lot like a spray of dark material that exited either when we set up a nitrogen purge right after the capsule had landed, or possibly because of the very tumbling sample return event. But this material was made almost immediately available to us to begin sampling, or to begin studying. And I'm not sure, I think some people have heard that it took a long time to actually get all the material out of our sample return capsule because we had a handful of screws that we needed to take off in order to access the majority of the material that got cold welded in space. But we eventually got there with NASA engineering a new screwdriver for us. So, but anyway, some of the earliest results from this material that was quickly available to us, we call it our quick look sample, revealed a lot of things that we had anticipated. And so when we were at the asteroid, we were able to observe some absorption features and reflectance spectra that indicated it was a very hydrated asteroid. It had this big absorption feature around 2.8 microns. And what we saw when we collected the sample was very consistent with a highly hydrated object. And so lots of indication of, water-bearing clay fibers, and then byproducts of aqueous alteration, a lot of magnetite in all sorts of forms. I love these beautiful iron oxide framboids that we have, just tons of pictures of. And then a tremendous amount of organic material as well. And so what I'd like to do, because I had so many questions about this today, is just talk a little bit about some of the most recent results that have, I'll quickly talk about this, but have been published by the OSIRIS-REx sample analysis team. So just last week we made the cover of Nature, and this is some of the Bennu sample. And what you can see in purple here is these needles of hydrated sodium carbonate that have been observed. And we see a lot of sodium-bearing phases in the samples of Bennu, lots of salts, some ancient evaporation sequences that have been preserved as well. And the sort of the broad brushstrokes of this are, this object clearly came from a very hydrated world, a world that was highly aqueously altered. To the extent that we see evaporation sequences of minerals, and towards the end, lots of salts that indicate there was probably a fairly large reservoirs of water that were allowed to, that evaporated either because of exposure to the space environment or from perhaps freezing. Actually, Paul Byrne gave me some ideas this morning about, what this, that it probably really was perhaps freezing, but I'm going to follow up on those when I get home. But in either case, that this precursor, Bennu's precursor, was likely something analogous to an ocean world. And some of the minerals that we've seen in these evaporation sequences are not too different from things like sodium carbonate that we've seen in samples, or excuse me, in spectra from series taken by the Dawn mission, as well as I believe sodium carbonate was also observed in the plumes of Enceladus observed by Cassini. And so perhaps indicates that some of these carbonaceous chondrites really did originate from things that are perhaps more akin to ocean worlds or mud worlds than we've typically thought about in the past. Another result I was asked about this morning was the finding of 14 of the 20 amino acids that are used by life in the Bennu sample. And so this came out in a kind of a companion paper in Nature Astronomy. It also came out last week. But that's a really exciting result. The chirality of these amino acids is also about equal right and left-handed, which might not be what people expect because the chirality of amino acids used by life is predominantly left-handed. And so sort of begs the question, okay, what happened? What happened to make life choose left-handed? So these results are very exciting. This is just the beginning of sample analysis as well. So it's, we are only about a year and 4 months, 3 months since the return, and we are just buried in data. But I'm super excited that these results have come out, and I look forward to what we'll be able to accomplish over the next year or so that the sample analysis program continues. All right, but what I'm really here to talk about is the extended mission for OSIRIS-REx. And this is a little bit of an eye chart, but the reason that I like to put it up here is because we are very fortunate. We had a spacecraft that performed phenomenally, and we had very few issues during our primary mission around asteroid Bennu. And so this right here shows the lifetime that remains on our limited lifetime items. And I think the story I just want to tell is that there's a lot of life left in this spacecraft. The thing that we had the least amount of was propellant. We had 27% of what we initially had when the mission was launched, but we still have a tremendous amount of fuel, even though it's a fraction of what we started out with. And so looking at all of this around the 2021 timeframe when we departed the asteroid, we started thinking about, okay, what could we use this spacecraft for next? And we did a lot of work at the behest of NASA to find the best possible target. So we examined several different near-Earth small bodies. We looked at Venus. We looked at some comet targets as well. And really the only thing we could do within 6 years of sample return was send the spacecraft to an asteroid called Apophis. And so I'll talk a little bit about, for me, this was like, I was stoked because Apophis has a pretty, it's a pretty big reputation among those of us who study small bodies, which I'll explain in a moment. But basically what happened is right after we released the capsule, about 20 minutes after we released the capsule, we went into a divert maneuver that is eventually going to allow our spacecraft, and I'll just start that over. Our spacecraft, which you'll be able to see in a moment in the orange trajectory, will eventually allow it to rendezvous with Apophis in the year 2029, right after Apophis makes an exceptionally close approach to the Earth. Now, we get our spacecraft very close to the sun in order to do this, much closer to the sun than it was designed to get, but so far so good. And so shortly after Apophis makes this very close encounter, our spacecraft will go ahead and begin rendezvousing with it. But a little more about Apophis for those of you who aren't in the business of studying near-Earth objects. You know, who cares? So Apophis was discovered in 2004, and the first set of observations, it was actually observed first at Kip Peak, which is not too far from where I'm located. And I would really like to talk to the gentleman that discovered it. I think, I'm not sure if that will happen, but I want to hear the full story here, because I've talked to a few people that were sort of in the small bodies community when it was discovered, and it sounds like it was a pretty fun time. So right after Apophis was discovered, it hit the highest place on the Palermo scale, which has, I'll have an update to this a little later, but those early observations indicated that there was about a 2.7% chance that it was going to impact the Earth on Friday the 13th of 2029. And so I guess, like, you know, how many folks are concerned about a 2.7% impact probability? Okay, so a handful. So the statistic I always like to remind people of is that in any given year, I think it's the University of Padova, their public health department had estimated before the pandemic, in any given year we have about a 2% chance of experiencing a global pandemic. Okay, so these sort of things can happen, but several pre-covery observations, so finding Apophis in sort of in observations that were intended for other targets, surfaced during the December 2004 timeframe, and basically beat down the probability that this was going to impact the Earth during the 2029 encounter with any substantial likelihood. However, until 2006, there was still concern that this near-Earth encounter was going to perturb the orbit of Apophis and then subsequently set it up for an impact further down the road. In particular, there was a lot of scare about an impact happening exactly 7 years later. But Apophis makes a lot of routine close approaches by the Earth. And so there's been a number of opportunities to observe it. And in 2013, based on these subsequent observations, the impact risk was calculated to basically be 0. And so we had a set of observations just a handful of years ago that removed it from the century risk table, and it has no chance of impacting the Earth in the next 100 years. However, the reason for all of that scare is because Apophis truly does get very, very close to the Earth in the year 2029. And so right here you can see its orbit traced out in pink. Here's Earth in blue. Here's the moon. Makes a pretty close pass by the moon too. And during this close encounter, the distance between the Earth and Apophis is 1/10 the distance between the Earth and the moon. So it's a very close approach. It actually dips below the orbit of geosynchronous satellites. Yes. No. Yeah, so Apophis it's not nearly as large as the Chicxulub impactor. It wouldn't cause global extinction, but it could take out a city. So it was an impactor that we think of as causing regional devastation. And I want to say the number that it's like 50 times more powerful than the most powerful nuclear weapon that's ever been detonated. So, you know, we would want to evacuate large swaths of a region if it was making, if it was going to make contact with the Earth, but we know with very, very high confidence that it will not impact the Earth in this particular close encounter. Go ahead. Mm-hmm. Its path would not be affected that close to the close encounter. there's actually been a few studies to examine what would happen to Apophis if we were to interact with it, kind of like the DART spacecraft, where you have a kinetic impactor, and you can put it into a potentially hazardous trajectory if you impact it before its close encounter on the time scale of, a year to 6 months. And this is, it's kind of wild, because there at one point, there's these annual Apophis workshops where we just sit down and talk about, okay, what are we going to do when this close approach happens? I put this up just so you can get a sense of the size across its longest dimension. And there's pretty big error bars on that, but within the scale of tens of meters. But yeah, I mean, at one of these conferences a handful of years ago, there was an idea put out there for a kinetic impactor of Apophis. And, there's no treaties or anything to stop this. So it's kind of crazy. The whole international coordination of Apophis is in, like, how the world is going to respond to it is its own. We could give a whole talk on that, because right now there isn't any, and there's a lot of people that want to observe it. And a really powerful radar, for example, could fry my spacecraft's comm system. So, anyways, I'm digressing. But yeah, this thing is gonna get close. And so let me see if there's anything I wanted to say on here. Anything else? I don't think so. Okay. But I like this graphic too. I think this frames what's going to happen during 2029 very nicely as well. So what you can see here is a 200-year time span, kind of roughly centered around now. And what you can see on the y-axis is the minimum close approach distance in terms of lunar distances of small bodies. And all these small bodies are just denoted by these circles. Their relative size is covered by the size of the circles. And then what that would translate to in terms of kinetic energy for an impact is what's shown on the heat scale. And so Apophis in 2029, it really stands out because it is the largest object to get so close to the Earth over this 200-year time frame. And really, something this large doesn't get to the Earth, doesn't get so close to the Earth, but once every 7,500 years. So, once nothing this large has gotten so close to the Earth in the course of recorded human history. We know that Apophis, it doesn't hit the Roche limit, so it's not going to get to the point where the tidal forces exerted by Earth begin to disaggregate it. And it does dip just below the geosynchronous line, but it kind of is within this ambiguous ranges of resurfacing limits that have been proposed by various members of the community, where you could expect material to mobilize on its surface in response to these tidal forces. And people have been sharpening their pencils on this a lot over the past couple years, because we really want to understand if we're going to be able to make out any surface change on the asteroid. So these resurfacing limits range quite a bit, and Apophis is within this ambiguity. We do know a couple things will change during the close encounter. Actually, Dan Shears, who I was speaking with this morning, did one of his students has done a lot of the modeling work to show that the rotation state of Apophis is very likely to change, very, very likely to change. For me, this is very annoying because I have to send a spacecraft to an object that I don't know what its rotation rate is going to be. So I have to build a lot of flexibility into how we're going to observe. And its orbit is also going to change. And so it is, the tidal encounter with the Earth will change the evolution of this object. Optical telescopes on Earth are not going to be able to observe Apophis shortly after its encounter, and so any changes in rotation rate will have to either be well characterized by radar, that won't be bothered by the fact that Apophis is so close to the sun, or spacecraft. And we're excited because studying an object right after it's gone through something like this, it's going to give us some it's going to allow us to address kind of a wide swath of scientific questions spanning from, just what is the material strength, what is the surface strength of these small bodies, how do they evolve in terms of tidal encounters with large planets, and also, address some questions about planetary defense as well. So Apophis is an S-type asteroid, so it represents that stony material that probably originated much closer into the sun. And it has a taxonomy that is sort of in between two different asteroid classes in this stony category that we think might represent freshly resurfaced versus very space-weathered materials. And so we're excited to go to this object to try and help resolve that conundrum, especially after it might have been resurfaced. But it currently has a very slow rotation rate, and its rotation rate, it has some non-principal axis rotation as well, so it has a bit of a wobble in its rotation. This is how its orbit changes from pre-encounter with the Earth to post-encounter. And so it gets further out from the sun as perihelion moves a bit, and that's just perfect for what our spacecraft can handle and do complex observations. So we're very excited about that. All right, so I'll try and wrap it up here. So there are 3 goals that we have proposed for the mission, and we are currently working on updating our spacecraft capabilities to achieve these goals. The first is, of course, centered around the close encounter. We want to establish the processes that drive the evolution of these small rubble pile asteroids, including and especially tidal effects from close encounters with terrestrial planets. So we want to characterize its rotation rate, and we also want to characterize the surface for recent evidence of surface change. And then we have a pretty impressive set of spectrometers that cover a wide wavelength range. And we also have gorgeous color imaging capabilities on our spacecraft. So this is just an example of the sort of false color data we were able to get at Bennu of its surface, highlighting the level of heterogeneity across the asteroid. And I've gotten this question a lot, which is, well, you designed a spacecraft and payloads for this dark asteroid with, variations that you expect were contributed from, perhaps varying volatile content. But we fortunately cover all the relevant wavelengths that we would want to be able to observe Apophis under. So this is an example of sort of the wavelength range that's covered by our visible and infrared spectrometer. And what you can see is Bennu in blue. We caught that absorption feature that's associated with hydrated minerals and hydroxyl around 2.8 microns. But at Apophis, this is currently our best near-infrared spectrum. We'll be able to catch this, the absorption feature that's associated with olivine and perhaps even pyroxene out, the second one over here. And we're actually pretty excited to look at these an S-type asteroid in these wavelengths. It doesn't happen very often, but of the few observations that do exist, we are seeing that there is perhaps solar wind implanted hydroxyl on their surfaces. And that has some cool implications for, did even these non-carbonaceous asteroids contribute some amount of water to the early Earth, and influence its isotopic composition, the isotopic composition of the Earth. And then finally, our third objective is to examine the properties of this potentially hazardous asteroid as an analog for other potentially hazardous asteroids. And so one thing that I'm very excited to do is repeat our thruster experiment, but intentionally. And so we'll be a lot more, we'll be designing this maneuver much more carefully to maximize how much of the surface we can excavate with our thrusters to really get at what is the near surface strength, what is the cohesion of this regolith, these properties very much influence how much, for example, momentum can be transferred by a kinetic impactor. And so with that, I think I'm at 50 minutes. I'll go ahead and close. Thank you all so much.
Thank you. I have 500 questions, but as a benevolent colloquium, I will open it up to our audience first.
Yep. So sorry if I missed this, but how soon after the Earth encounter do you get there, and how long can you stay? How long do you think you'll be able to continue rendezvous operations?
Yeah, it's a great question. So we begin observing Apophis, but it'll be all disk integrated observations about 2 weeks before the close encounter. So we expect to get light curves to sort of see how the rotation rate, how it is, and then sort of what happens after the close approach. But our resolved observations won't come until about a month after that. And then we say we arrive, although arrival is kind of arbitrary, at Apophis in June of 2029, and that's the point where we have to start maneuvering the spacecraft around the asteroid. So its small amount of gravity will be influencing us. So I didn't talk about it here. In fact, I swapped out some slides to talk a little bit more about the Bennu stuff in response to questions I got earlier today. But we are very much hoping for an Apophis pre-encounter mission. And so Ramses, which is this mission concept, I think they just passed their PDR, that is being developed by the European Space Agency, represents perhaps an opportunity to fully map Apophis before its close encounter so that we could truly do pre and post comparison observations. At Bennu, we found signs of recent mass movement, and all of our inferences of what was recently resurfaced material were shown to be right when we actually interacted with the surface during sampling. So I think we were able to convince NASA we have a plan to look at areas of interest that would perhaps be indicative of recent resurfacing, but we won't have that pre and post comparison set of data unless there's a mission that gets there before the close encounter with enough time to fully map it. The Janus mission is also perhaps another opportunity to do this. And so we would love for NASA to find a home for those spacecraft. But yeah.
Hi there. I'm Kaya. I'm a grad student, and I actually worked for Janus, so it's great to hear it mentioned. But in terms of reshaping, so obviously that's a big question for this mission. I can imagine there's multiple different ideas about how we'll determine what reshaping has occurred, but I noticed you had YORP estimates. Do you expect to be able to differentiate between changes to YORP that result from orbital changes as opposed to ones that might result from, or a YORP change that might come from bulk reshaping?
That's a good question. I'm not sure that we would be able, my understanding is that we don't expect there to be large-scale reshaping of Apophis. There might be some interior reconfiguration, and that would, of course, play into how the rotation rate changes as well, right? And so I'm not sure that we will be able to distinguish things at that level. Off the cuff, I'll say I don't think we can, but I might be wrong. But it's everything that I am aware of in the literature, except for some sort of pathological cases, seems to indicate we can really only expect centimeter, maybe at the in the most pathological cases, meter scale changes on the asteroid. So if we do have the opportunity to do pre and post observations, they need to be high resolution. And OSIRIS-REx, the OSIRIS-REx spacecraft is capable of doing those very high resolution, like centimeter scale observations that should be able to reveal this change. But we will need pre-encounter images that sort of match that quality. The other possibility here is that I know the Ramses spacecraft is very much hoping to deploy 2 CubeSats to the surface of Apophis, one of which would include a seismometer. And I've participated in a few studies to look at sort of the seismic response of Apophis during the closest encounter. we should get a pretty robust seismic response. So that might be the best way to really work out, what level of interior reconfiguration might take place.
First of all, thank you for the great talk. I will resist the urge to ask you about 5,000 questions rooted in anxiety and instead ask you, and I apologize, this is an incredibly naive question. Is there anything, and if so, what sort of things can we learn about protoplanetary disks, or at least our own, from asteroids rather than understanding the planets in our solar system?
So, I think maybe, I'm just going to spitball a little bit here. Yeah, so we are starting to pull together a picture that when these rubble piles come together, it's a very slow process. Like Bennu is truly a pile of rocks, and everything, there does seem to be some internal stiffness, but everything that we've learned from interacting with it and sort of the models that try to, characterize how you can get these very diamond or top shaped like small asteroids, indicate these are small sort of accretionary events. So I wonder, and I don't know, so far out of my expertise, but I wonder what we can start maybe pulling together about sort of just basic planetary accretion. Like how do these models, if you sat down with somebody who does these rubble pile accretion models, somebody who models pebble accretion, like what are sort of, where are there some things that overlap? And because a lot of the models, my colleague Patrick Michel has done a lot of this work. They're really tuning their models to get these shapes. So it's an observationally driven set of model constraints that get pulled together, and there's so many unknowns. So I kind of wonder what type of emergent behavior comes out of using your observations to really tune in your models, and maybe how can that be applied to other accretionary processes?
Yeah, go ahead.
Oh yeah, these for sure. Mm-hmm. Yeah. Yeah, and I should clarify. The accretion of Bennu was probably kicked into the inner solar system about 2 million years ago, and then I want to say its parent body was disrupted on the order of about 2 billion years ago. So we're dealing with, we don't have a disk, right, at that point. To push things together. Yeah, yeah, yeah. Good.
We have more, so we're gonna keep. We've got a few more. We had 2 up here. Oh, that way. Okay, 1, 2, 3.
So you were talking about essentially how you were with respect to Bennu, as to how the surface was different from what ground-based observations had revealed. Could you dwell a little bit more on what the discrepancy there was, and how you expected it to be rockier, and if the same thing is now informing the Apophis encounter?
Yeah, so that's a very good question. So there's a couple ways, a couple key ways that we just missed the mark with Bennu. But I would say from my perspective, at least the most substantial one was we had obtained Bennu's thermal inertia from the Spitzer Space Telescope data, and that indicated that it had a relatively low thermal inertia, and so we had inferred that, and I guess, just to make sure everybody's on the same playing field here, thermal inertia is just this measurement of how quickly something heats up and cools down. So you think of a solid boulder just sitting in the sun. In the morning, it's going to heat up very slowly, and then at night, it's going to radiate that heat very slowly. And the reverse would be sand on the beach, right? It heats up really quickly during the hot day, and it cools down really quickly at night. So Bennu had a thermal inertia that, based on everything we have studied from terrestrial materials and formed by thermal emission spectra from the surface of Mars as well, that indicated it was composed of very fine-grained material that heated up quickly and cooled down. And I think we estimated that it had a 2-centimeter average grain size on its surface, which is why we had that 3-centimeter opening in our sampling mechanism. And that just didn't turn out to be the case. Bennu's material is very low in thermal inertia, but it's extraordinarily porous. And so we had these big boulders that were highly porous. It's the best explanation we've come up with to date. We are planning to do a lot of thermal physical analysis of the sample to try and close the loop on this story, and we haven't gotten to that in our sample analysis campaign yet. And there's some other observations that were made that were they made more inferences. Radar data from Arecibo indicated that the circular polarization ratio was consistent with a fine-grained material, and there was some red spectra that were taken more the equatorial zone on Bennu that were probably just noisy, but were at the time interpreted to mean that maybe there was a concentration of fine-grained material at the equator. So those are some of the lines of evidence that were incorrectly, like they ended up not being consistent with what we found when we got there.
Great.
Question about Bennu. Given the number of amino acids necessary for life that were discovered, was there any evidence of carbohydrates? And if not, would you expect to find any?
I cannot confidently answer your question. I will just say I have had I do not have a biology background, so I have been fortunate to learn as I go as the sample analysis campaign gets further and further from my expertise. I will say that we have found a lot, we found a number of sugars, and we found let me see if it's in my notes actually, but I will be happy to redirect you to some of the papers that have been recently published on the organics. Let's see, we found all 5 of the nucleobases that life uses on Earth to transmit and store genetic instructions. But yeah, that's all I got for now.
More to come. All right, there was one.
Thank you for your talk. It was really interesting. I apologize if this was touched on in the literature. I haven't read up much on it. Can we now, with the trajectory and the different, the sampling, infer where Bennu comes from, and more accurately, since we have maybe with dating, with carbon dating, or I don't know, what type of method, find the ocean world where originally it might come from?
Yeah, so we have a good handle, just based on the orbit of Bennu alone, on what its candidate parent bodies would have been, which are, there's 2 asteroid families in the inner main belt that represent the most likely origin point of Bennu. And so the parent asteroids, Polana and Eulalia, are thought to be the most likely candidates for where Bennu would have originated from. They currently reside in the asteroid belt, probably formed further out in the outer solar system, and then were scattered in, likely during one of the giant planet migration events. But we have relatively high confidence that one of those 2 parent bodies is likely the origin of Bennu. And actually, Bill Bodke at SWIRI is the person who has done a lot of that dynamical unwinding to lead to those results. So.
Okay, with that, I'm going to wrap it up. Please thank our speaker. Thank you so much. I will see you next week. And by the way, coffee is moving, so keep an email out for that. So our coffee hour, the 30 minutes beforehand, will be moving. We will send an email. Thanks so much and have a great week and take care of yourselves.